Hello students, in this video we'll prove the Heisenberg Uncertainty Principle using the Fourier transform. So the Heisenberg Uncertainty Principle states the following mathematically. It states that the integral over r of x squared phi of x squared dx times the integral over r of xc squared phi hat of xc squared dxc. The product of these two expressions is always, for any reasonably smooth function, bigger than or equal to some constant c0, which is not 0. Okay? All right, excellent. So what we're going to do is let's state the assumptions of this, right? We're here, phi of x is sufficiently smooth and rapidly decaying at infinity. At plus minus infinity, right? So in particular, typically we think of phi as a Schwartz class function. Schwartz class will work here. And the other assumptions, we're going to make a normalization assumption. I'm going to normalize this, so phi must be sufficiently smooth and rapidly decaying, and I'd like to normalize this so that the integral over r of phi of x squared dx is equal to 1. If I make this normalization assumption, then by Plancherel will say that this integral over r of phi hat xc squared dxc will also be 1. That's by the Plancherel theorem. Okay, and that says that both phi squared, modulus phi squared, and modulus phi hat squared are probability density functions. So hence, we're going to assume in this problem that phi of x squared and phi hat xc squared are probability density functions. Okay. And the physical interpretation of this is the following. So physically, the probability a particle is in AB is going to be equal to the integral from A to B of the phi squared, and the probability the momentum of the particle is in AB. It's going to be the integral from A to B of phi hat xc squared dxc. So both those are probabilities because I know that both these functions integrate to 1 over the entire real line. So these are actual probabilities, right? So in other words, what the Heisenberg principle says is these things represent up to a shift represent the variance. So the variance of the position of the particle times the variance of the momentum of the particle are always bounded above. In other words, you cannot sharply localize both the position and the momentum of a particle, and that's what the Heisenberg Uncertainty Principle says. So that's the physical context of the problem. Let's prove this under this assumption over here. So how does the proof go? So we're going to use this assumption over here. So here's the proof. 1 is equal to the integral over r of modulus phi of x. Okay, I'm going to integrate this by parts. This is going to be my dv, and this is going to be my u. So if we integrate this by parts, what's going to happen? This is going to be u times v, so that's going to be x times modulus of phi squared over r, minus the integral over r of v, which is x, and then du, so that's going to be the derivative of phi of x squared dx. Okay, excellent. Now by the fact that phi is vanishing sufficiently rapidly at infinity, both those limits are going to be gone. And so we have, now we can just, I'm going to use the product rule on this thing over here. So this is going to be equal to negative the integral over r of x, and then times what? And then it's going to be phi of x, phi prime bar, plus phi of x bar, phi prime of x dx. Okay, and so therefore, by just the ordinary triangle inequality, 1 is less than or equal to twice the integral over r of absolute value x by putting the absolute value on the inside of this times what? Times 5x times what? Times 5 prime of x dx, okay? Now I can use Cauchy-Schwarz on this. So by Cauchy-Schwarz, this is going to be 2, the integral over r of x squared 5x squared. So that's going to be my first function, I'm going to Cauchy-Schwarz dx to the power 1/2 times integral over r of just a 5 prime of x quantity squared dx to 1/2 power. Okay. Now I can use Plancherel on this thing over here. So if I use Plancherel, I know this is going to be the same. This is the L2 norm. This is just the L2 norm of 5 prime. And so that's the same as the L2 norm of the Fourier transform of 5 prime. Okay, by Plancherel. And so, but what is the L2 norm? What will that turn into? So this is going to be what? This is going to be equal to, less than or equal to, 2 integral over r of x squared. I can drop the modulus over there now. 5x squared dx to the 1/2. And then, of course, the the Fourier transform of the derivative is going to be a 2 pi. So I'm going to be able to pull out a 2 pi. And then modulus 6c squared, right? So this is going to be a factor of 2 pi squared, but it's homogeneous, right? So I can pull that out, pull the 2 pi squared out. So I'm going to get 2 pi. And then integral over r of what? Of xc squared, phi hat xc squared dxc to the power 1/2. Okay? And so then rearranging all this over here, we can see therefore that this, so 4 pi times this expression is always bigger than or equal to 1. So I can say therefore that what? By throwing the 4 pi over here, this quantity over here times this quantity over here squared is going to be bigger than at least what? The square of 4 pi squared, right? So in other words, we have this expression. We've proven therefore that this expression over here, by throwing the 4 pi over here, so I can get rid of that and get rid of that and put a 1 over 4 pi over here, right? So 1 over 4 pi is less than or equal to this thing to the 1/2, this thing to the 1/2. So this number over here squared is going to be less than that times that. So that's going to turn into a what? That's going to turn into a 1 over 16 pi squared. And now we're done, right? So we've shown actually therefore that what? That the L2 norm of these expressions are going to be controlled, right? And so the final version of this is that you can say that there's a constant c, so hence, by modulating and translating this function over here, we can see that there's a constant c such that c is less than or equal to the integral over r of x minus, I'm just going to say mu, for any constant mu, phi of x module squared dx times the integral over r of xc minus mu hat squared, of course, right? Squared, phi hat xc squared dxc, okay? In other words, the variance of the location of the particle times the variance of the momentum of the particle cannot multiply, give you something small. So they both can't be, if they were both able to be small simultaneously, I would not be able to find such a constant. So they cannot both be sharply localized. And that's the Heisenberg Uncertainty Principle from the Fourier analytic perspective. Thank you very much.